Oh, okay. That was close. So many times in the past, I've gone through the whole lesson and then I realized in the end, I had not recorded. Okay. So the purpose of this experiment is essentially to use the freezing point depression to find the molar mass, in this case, of an unknown, right? Let me zoom this out a little bit so we can see. Yeah, molar mass of the unknown. Now we know the molar mass unit, the molar mass has a unit of grams per mole, right? And so it says here, of course, you're going to be using the freezing point depression method of a pure freezing point temperature of pure cyclohexane. Cyclohexane will be the solvent, and then the unknown will be the solute. So you figure out the freezing point of pure cyclohexane. And I gave you two data points, or sorry, two data sets as though you actually did it in the lab. So your lab work will essentially produce these two tables here. The table on the left, and this would be pure cyclohexane freezing point temperature. You do the experiment and measure out each of these temperatures. Sorry, I'm realizing that my screen is a little large. I want to make sure you guys can see it. Yeah, so you sit in the lab and then do the work to produce these two data sets right here. Okay, let me minimize that. Okay, so now we're assuming your lab work is done. This is the solvent only and the freezing point, and this is the, oh no, mine is messed up. Why are these the same? Okay, sorry. Let me see if the one I sent you guys is correct, because the solution has to be lower, right? The law states, the colligative property essentially states that when you have a solute in a solvent, the freezing point is lowered. Let me see, how do I go back and find what I'm looking for? Yeah, hopefully the one I sent you guys was correct. Because the one I'm looking at over there is a duplicate. I have the same table twice. Let me find that right here. Okay, I'm looking for this student copy. Okay, yeah, this is what I'm looking for. You see, this is lower, right? Yeah, this ends on like about 6.3, this lower. Okay, this has the correct format. Now, how do I save this? File. I'm gonna try to write on this and do stuff to it. So, oh, will it not allow me to download? Are you guys able to download this and then save it? Oh, there, save as. Okay. It's just my computer that's being slow. Download as a copy. Fine. Okay. I was trying to figure out why it wouldn't let me. So yeah, if you download it, you can actually save it on your desktop, then you can do stuff to it. I just don't want you guys to modify the original one, right? So I kind of gave the summary of what you're doing here. So hopefully, oh, there it is. Okay. This is what I'm looking at right now. Yeah, excuse the mess I have in the back there. Yeah. So we have these two data sets as though you've actually done the experiment and you're done, right? So you have the pure cyclohexane on the left, you have the cyclohexane and the unknown mixture on the right. As we said, when you have the solute, in this case, this part right here, the solute, the unknown, added to the solvent, the freezing point, it decreases, right? So you can see how the freezing point on the right is relatively lower. Okay, now let me go ahead and find the directions. I do apologize for all the stuff I have going on, but this is, let me see. I have to find the document I was looking for. Let me just close this one out because I feel like it's just confusing me. So I'm going to be writing on this. Let me close this one out. Okay. Does anybody have any questions so far? Okay. So I need to find the document where I had, this is a maze. It's like a maze. I need to find a document where I have the actual lab. I'm trying to read that part. I'll find it in a moment. Okay, this is what I'm looking for. Oh, no, not that one. This one here. I know this happens in all my recordings. I keep losing documents. It's around, because I already downloaded it, so it should be around here somewhere, but for some reason I cannot find it. Oh, come on. Okay, it should be here. Okay, there it is. So, of course, we're going to be using this formula right here to figure out, from the experiment, we'll figure out delta T, TF, right? So remember, we do have the freezing point of the solvent, the freezing point of the solute, and I'll draw that and show you how I read the freezing point from the graph. And then once we find the difference, we're given the KF from this, yeah, from this graph. So I'll show you where things are, okay? So delta T comes, this part here comes from the two graphs I showed you. Kf is given to us, and then we're going to be using that to find molality. Once we find molarity, which is going to be the solute, the solute moles, or the moles of solute over a kilogram of solvent, we can use this information then to eventually find grams over moles of solute. So from molality with the L, we'll get moles of solute, right? We'll use this part here. If we have the mass of the solute, take the grams of the solute divided by moles of solute to get the molar mass. And of course, it kind of talks you through the whole process, which this is just information because I didn't want to change too much. But this is showing you step by step what we're going to be doing. So our plan right now, since I have the graph, is to number one, determine the difference in the freezing temperatures. So I have to draw the graph, number one. So you guys will draw the graph. I'm just showing you how I'm doing it on my end, but you have to, I want to say go home. You are at home. You want to draw your own graph, both of them. You can combine them on one graph paper or do them separate. Then from there, you figure out the freezing point temperature, and I'll show you how to do that. Then once you do that, you subtract the 2 to get delta TF. So here they're showing you delta T is essentially T1 minus T2. T1 is the freezing point of the pure cyclohexane, the solvent only. T2 is the freezing point of the mixture. That will be a lot lower. Remember, delta TF has to be a positive number. So the higher number minus the lower number gives you a positive number. Once we get that, we use that number in this formula here, knowing what Kf is to find molality. So this is a step by step of what we're going to be doing. We'll find the kilograms of the solvent cyclohexane, use that to find the moles of the unknown solute. Once we got that, we got the moles, we'll pretty much have the molar mass by taking grams over moles, okay? And then here they're showing you that, of course, we have to do percent error. And so I'm going to walk you through all of this, okay? And just in case we have the units here, units for each measurement, molality, moles of the unknown, molecular weight or molar mass that we figure out from the experiment, and compare this with the actual. So, oh, and then just in case, I posted that table here again. So the table that you saw in the Excel spreadsheet, it is right here again. It's the same table, same information. It's just here is a more linear fashion. Okay. So I really want to work on the Excel spreadsheet because I can draw the graph from there and y'all can see how I draw the graph. Okay. So let me get out of here and go on the Excel spreadsheet. Because of the way this is, I don't want to combine the two on the one graph paper. I'm going to just draw it right here. So it does say here in the directions, I kind of pulled this from the lab itself. You're going to be drawing two cooling curve graphs. And it says you can draw it on an Excel spreadsheet if you want. The graphs will be curves, not straight lines. Use the data provided above, and this is as though you've done the experiment. Graph will be used to determine the freezing point of solvent and solution. So I'm going to start with the solvent only. You want to highlight the numbers. When you're drawing a graph on Excel, you put the x-axis first. So the Excel program assumes the first number or the first column you have is the x-axis. The second one is the y-axis. So if you do it this way, then you go to Insert, So I've highlighted this, right? Go to insert. And by the way, if you know how to do what I'm struggling to do, you can always help me out. I'm always open to learning. I'm gonna insert. Hold on a second. Let me see if I can make the screen a little bit bigger so y'all can see because I'm standing right here. I know what I'm looking for, but it's a little hard to see. I'm trying to make my screen bigger. Let's see. Command. We're not getting bigger. Oh, only this part is getting bigger. So I'm trying to draw a graph. So I went to the insert right here, and I'm selecting scatter plot. So if you see right here, scatter plot. Okay. I'm going to cover this for right now. I don't need the stuff in the back, so I'm going to cover it so y'all can see the graph. Hopefully you can see the graph. And this is where I struggle, right? I'm trying to, this is the full cooling curve. It's called a cooling curve because it's a freezing point depression. We start with a liquid and then we form a solid, right? From liquid to solid, that is cooling. We're trying to find the freezing point temperature. And the freezing point temperature, the way you're supposed to figure this out, you draw a straight line from the beginning point. So the straight line will go through the first few points, like right here. So the part where I'm struggling is how to separate the beginning points from the final points. Now, I watched this guy do this on YouTube video. You know, you can learn anything on YouTube. I mean, you can learn if you have time, and I don't have time. So I'm just going to partially show you what the person did. Let's see. Yeah, having the series. I don't know what they did, but they went on here. You see how it says series 1? I don't know how to add series. It says delete series. I just don't know how to add series, but you're supposed to be able to add. I won't figure it out right here. You're supposed to be able to add series here, and then. Oh, is somebody gonna help me? Because that would be very exciting. Hold on, I have to go back to this part here. Oh, I thought y'all
Yeah.
were helping me. Okay, that's fine. Yeah, you need to download it because I'm sharing these files. I cannot allow you to edit the original file I gave you, so you have to download it. There should be a place either download it or save as. Okay?
When
Wait, so
you
you're
right
just trying to.
click, oh, when you right click,
No,
do
go
you
ahead.
see
Yeah.
something that says setup?
Oh wait. Okay, so you're helping me with, okay, hold on. Before you start helping me, let me make sure that people can download. Was somebody else asking something? Or were you all trying to help me?
Oh, I was just trying to confirm like what we're trying to do. So we're just trying to draw a line from the first point down to where it reaches the freezing temperature.
It's about halfway, like around 120. So it's, yeah, we're trying to draw a line from like down here to maybe like down here. And then we're gonna
Oh,
try draw another line
I
from.
in order to do that, I think if you click, are you trying to figure out the series or do you want to do the line?
I'm trying to figure out the series because if I can select and add two series to the one graph, that will help me to plot the lines separately.
So if you right click, there should be something that says setup. Is that
Okay, so
there?
right click on the data or on the
Yeah.
table.
On the data.
Okay, so right here it says
Or
reset.
maybe right click on the just the graph.
Oh, select data. I think this might be it. Okay, so
And then there should be something that says add axis or series set under there if you see setup.
okay, I think this would be my first one. Uh,
So
this
I
is
think
series 1.
press the like the plus button at the bottom, I think. Like
There's a
in
plus button.
right, like where it says switch row/column. and then to the yeah.
Oh, thank you very much. You have no idea. I've been standing here trying to figure. I was watching the YouTube video and I was like, this is not enough. Okay.
Yay.
So I'm trying to select this data range. That would be from here to here for the second one. Oh, now it's saying it's not valid. This is to an open worksheet. No, it's not. It's not working. Okay, it didn't really allow me, but what I'm trying to do here, which it might be complicated if I'm, yeah. So this point here is part of the first data set, right? From 15 seconds to 120 seconds. For my second one, I want to add this to the first one. Anyway, whatever it is, I think I have to kind of do this over again. Oh my goodness. Okay. Delete this whole thing. Because for some reason, I think I just messed this up. Yeah. So I'm going to start from here. So from here, I select all that. I think you helped me, but I need you to just be on standby because as quickly as I learned it, I'm going to forget it. So I go from here, insert, not draw, insert a graph. So scatter plot, click on that. This is my whole data set, right? But all of this is seen as one data set. So I want the first half of the points to have its own best fit line and the second half to have its own best fit line. And that was the thing I was struggling with. So we said while I was out here, I should right click and then was it select data? Yeah. And so about this part, right, will be the first series. And then when I'm done with that, add the second series. And second series should go from here to here. Let me see if that works. Add it to the second series from here. I don't know why it's not really allowing me. Yep, it's not working. Anyway, so let me see if I can do this manually. Let me copy this.
You could also try to make them into two separate columns, like series 1 and series 2 in Excel. So they're like so technically it would be like 4 columns, I think. And then you could
I see what you're saying.
color them
And then have them on the same graph?
Yeah, you can.
Oh, okay. Let me try this one. This is the one last thing I'm going to try, and after that, I'm going to give up. I see what you're saying. So what you're saying is, yeah, I've never been great at this stuff. So let me try to see. I'll make it on a different page completely. Because I'm just what if you're wondering what I'm trying to do, I'm just trying to plot the graph and show you what needs to happen here, which is so much easier to do it manually. But what I'm doing right now doesn't seem to go easy. So let me try to. That's why I teach face to face. Okay, so what you're saying is, let me insert here and insert here. You're saying take this second, the part that I want to break up. Is that what you're saying? Am I getting this correct?
Yeah, that's what I'm saying. And then like in column B row 1 or whichever way you decide, like um say series 1 for the 15 to 120, and then I would say series 2 for the 15 to 330. I think that would work. If you would want to wrap the text, I think then that can kind of
Whoa. Okay. Hold on. Like I'm hearing the words, but I don't know what to do. Okay,
Sorry.
hold on a second. Yeah, no. I'm hearing what you're saying. It's just when I get nervous, it's hard. So let me try a more a less labor intensive way of doing this. Let me see if I can copy the graph and paste it on Word. if I can if I can draw the, or maybe even do it right here. Let me try the simpler way, because I hear what you're saying, but I'm already getting nervous because I'm like, oh no, look at all this time that's passing.
No, that's very
So
fair.
yeah, but then what
I'm
I
gonna
can do is when I'm done, you can show this to me later. So what I'm trying to see is, let me see if I can draw on here, because if I can draw on here, it will help. Can I draw on here? Okay, I'm trying to do this. This is what I'm trying to do. Okay, maybe not that like that way, but it's more like, yeah, the best fit line for the first few data sets. It's gonna be something like this.
um
And
okay.
then for the last few data sets, can y'all see? It's gonna look like this. It's gonna be a lot straighter. Okay?
I think
And then
the
where
thing
these intersect, this is your freezing point. So you're gonna read this number over here, whatever this is. That's what I'm trying to do. It's just the person did it on video. It was so cool. I'm like, oh, I want to do that. Then I couldn't do it. So can you all see that? So that's the freezing point for the first graph. So you do it for both graphs, and then I guess it works out. This is so much easier. My goodness. I mean, there's a proper way to do it, Excel stuff, but y'all saw me just fall apart. Yeah, my husband always looks at me like it's not that difficult. I'm like, I don't know what to do. Yeah, this is what I was looking for right here. So you kind of have a best fit line, and you want to, as much as possible, just kind of draw a best fit for the first few sets of data. You might draw this a little bit more horizontal because, or a little bit more diagonal, I guess, because it's more like, you can do it a little bit more like this. Ah, it's hard to draw that. Yeah, the first one's a little bit harder to draw, but it's something like this, right? And then yeah, so you have some on this side, like this is on this side, you have some on that side. And then where they intersect, that's the freezing point. So I can't tell exactly what this one is. Uh, this halfway through will be 7.5, right? So this is below 7.5. What do we think it is? Maybe like 6.3, maybe 6.2. I don't know. I'll pick a number, 6.2. I'm just trying to estimate what this is. Okay. So the freezing point of this one here is 6.3, 6.2, a little bit. It's, or maybe even 6.4. I don't know. Look, it may be a little bit above this one here because it's not exactly on this line, right? Slightly above it. And then over here, you draw the other one again. You can draw them both on the same graph. And if you want to do it that way, that works too. So I'm going to show you how you can do it that way. How do I get out of this draw feature? So what I'm going to do here is delete this. I'm going to try to combine both graphs at once, okay? So if I do it that way, I'll delete the whole graph right here. Let me erase all of this. So if you draw them both together, you have to have these numbers like that. Insert, since you're going to be drawing the graph, select the data table where you're going to be drawing the graph. Oops, why is this still showing? Okay, so stop the draw feature and then allow me to go to insert. So insert graph for this whole thing right here. Okay, finally I got this right. So when you have this right here, it shows you both the pure part and then of course the solution part. So you have your X, you have your two Y's, and these are it right here. Okay, so you have your pure, I think that's on top because that's a higher freezing point, your solution on the bottom, right? So I'm just going to show you how to manually then, of course, like I did before, draw the freezing point. For the first one, supposed to be straight. And that's supposed to be straight too. So I feel like it's slightly, the way I drew it here, maybe 6.4, something like that. And this is the freezing point of cyclohexane. And I need that on the next table, right? And then down here, I'm going to use a different color because I don't want to confuse the two. Let me use the color, the black color. Okay. This is straight too. And then here. Okay. For this one here, I'm thinking 4.5. Now I'm just making these numbers up. I'm not even using a ruler, right, to do that. So this is going to be temperature freezing of solution. Okay. So I need this. I'm going to write this on my tablet. Temperature freezing of cyclohexane, 6.4 degrees Celsius. Temperature freezing of solution is going to be 4.5 degrees Celsius. Okay. Now that I have this, let me go to the next page because I did all my scribbles here. I'm going to go to my next sheet right here. So we're going to get out of the drawing feature, click that, and then back to this. Okay, so now that I have this, from the experiment, the volume of cyclohexane we measured was 25 milliliters. So you need this data now. Density of cyclohexane, we have that here. Mass of unknown solute is written here. Freezing point depression constant of cyclohexane is given to me right here. From the graph, I need freezing point of cyclohexane. I think I said it was 6.4, right? Degrees Celsius. So degrees Celsius. You're going to write degrees Celsius here. So I'm just going to put 6.4 C. And then from the mixture, I got 4.5 also degrees Celsius. Let me see what the difference is. Now I made up these numbers, 6.4 minus 4.5. Oh. That's okay. I'll go with those numbers. And so the difference I got here was 1.9. I'll say to get this better, I'll say you should print it out and then get those numbers manually because somehow I just feel like this is a little bit too small. But anyway, this is what I got for right now, 1.9. Okay. And so I don't know why this one's a little bit lopsided. Okay. So now we're figuring out the mass of cyclohexane and fill it in the rest of these, right? So how do you think we'll find the mass of cyclohexane? Let me pull this up here. Look at the data you have in front of you. We have the volume of cyclohexane, we have the density of cyclohexane, we have the mass of the unknown solute, we have the freezing point depression. This is of cyclohexane. How do we get the mass of cyclohexane in grams? Of course, in the same mass. In other words, we want the grams of cyclohexane. How do we find that? Does anybody have any idea? Okay, let's see. Okay, so what you're gonna do here is divide what by what? Okay, so what you're gonna do here is, we don't need this one here right now. What you're gonna do is, you want to get grams by itself, right? That's how I usually look at it. If they say find mass of cyclohexane, find a number that has a unit that has grams in it. Do you all see which one has a unit that has grams in it? And it's linked to cyclohexane? I know it's lab, but it's still the same stuff. It's kind of the same stuff we're doing in lectures. It's kind of masked a little bit. But you have all these numbers here. Right now, I only see two numbers that have grams in it, and only one is associated with cyclohexane. You know? I know, I know. I just had that screen. Where did I put it? Oh, there it is. Yes, grams per milliliters. Dominic, the 0.37, that's a grams, but it goes with the unknown, not cyclohexane. So this one here is a better choice. Okay? So for that reason, let me go back to, I hope you get what I'm saying, right? We're looking for a number that has grams in it that goes with cyclohexane. So based on that, from these two, we got a delta TF as 1.9 degrees Celsius. Okay. Next thing we're trying to find is mass in grams of cyclohexane, which is just saying that get a number that has a unit grams where it's talking about cyclohexane. Okay, the closest thing we saw was from the table where we have density, but density is not grams. That's okay though, but it has grams. Density of cyclohexane. So why are we picking density? Because even though it doesn't have gram only, it does have gram. So 0.779 gram per milliliter. We don't want the milliliter part. We don't want this part right here. We just want the gram part. Okay? So how do we use the density to get the grams? How do we get rid of the milliliters? Think about dimension analysis. How do we get rid of the milliliter? We have 0.779 grams per milliliter. We get rid of the milliliter by doing what? Okay, I heard somebody say something. If you divide by 1,000, I'm assuming you're going to make it kilograms. We're trying to get rid of the milliliter. So look at the number in the table. I know it's somehow because this lab is different, right? Look at the numbers in the table. Do we have any other number that goes with cyclohexane that may have a milliliter unit that actually has a milliliter unit? The volume, right, right. I know you guys don't have a connection with these numbers because you didn't do the lab yourself, right? I feel like it would be a little bit easier if you did the lab yourself. But we're just using dimension analysis here. We're trying to get rid of milliliters to get grams. For us to do that, find a number, in this case, the volume of cyclohexane. So take this number, multiply by 25 milliliters, because this number here is the volume in milliliters of cyclohexane. We can use that number to multiply by this second number to get grams. Okay? That gets rid of the milliliter. And we get a number in grams. So I'm going to multiply this out. So I gave you all the numbers you will need to complete the task given. Okay, 19.47. No, you have to multiply it, not divide. Yeah, you have to multiply, not divide. So let's look at this. If you multiply, then the units are in a position to cancel out, right? Here I have 1 milliliter, here I have 25 milliliter, and then yes, it cancels out like this. If you divide, let's try out the dividing. Then you have milliliter here. Divide by milliliter is the same thing as multiplying by 1 over milliliter. All it does, it makes the situation worse because now you end up with grams per milliliter squared, right? So this is not going to work. We want gram only. So that's going to work. And yes, it's 19.475 grams. Okay. So I'm going to go ahead and put that in here. 19.475. Okay. So I got that. Okay, good. So we're here. Now they say find the molality of solution. This is that little m, right? The little m, that's not mass. Okay. Since the context here was the experiment was about freezing point, that's going to be delta TF equal, well, I, right? We learned to use I, KF times M. But in the dialogue of the lab, they already said this unknown, which we don't know the formula, is a molecular compound. So I is equal to 1. So we can just kind of drop off the I and move on without it. We're back to that original formula. Okay, we're trying to find little m, right? So to find little m, that means divide by kf, divide by kf. So you have, it's a little crowded in here, delta tf over kf equal m, okay? Now, oh, we already have delta tf. We said back here it's 1.9 degrees Celsius. Just so you know, I'm not happy with that number. It's just based on how I drew the graph. But if you use a ruler for the bottom part, it will give you, the number is supposed to be not exactly, but close to the, just in case you're wondering, it's supposed to be close to this one here. Like this one here is close to 6.3. But that one, because it slopes a little bit, when you draw the best fit line, it's going to be closer to the threes than it was to what I was reading right here. Okay. So the gap between these two is supposed to be higher than 1.9. But based on what I got, I'm going to continue with that. So this is over KF over here is this number 20.5 degrees Celsius over M. This and this cancels out. The bottom of the denominator is a numerator, or the denominator of a denominator is a numerator. So the answer will be M. Molality will be some number M. So I have this divide by 20.5. I get, do y'all get 0.95? Like 1.9 divided by 20.5. Oh, did I press something here? Okay, that's what I got the second time. Like, okay, great. So we got this. So I can go back and put this in the table. Once again, you guys will have to work this out. 0.0926. Okay. Now we have to get the molar mass of the unknown solute. Okay. The molar mass, we know based on all the stuff we've been working on, the unit has to be grams per mole. So you want to get the gram value, divide by mole. If you go back here, we haven't used this number yet, right? So I'm going to highlight this here. We haven't used that yet. So if we can get the moles of the solute, we can take this number 0.37 grams and divide it by that moles, and we can get this number. Then we'll be good to go. Okay. The thing is that we have to find the moles of the solute. So back to this. We know that this is molality, right? The formula for molality is moles solute. Ooh, what we're looking for over kilogram solvent. Okay, so we're looking for this. Like, what is this? To get moles solute, I'm going to put over 1 here so we can cross multiply. I'm going to do this part first and then the other part. Moles solute is equal to molality times kilogram solvent. So I did that part first and this part here second. So moles solute equal to little m is 0.0926. And of course, molal with the L is moles over kilogram, right? So when it says here kilogram solvent, do we have the grams of the solvent? Oh yeah, we have the mass of cyclohexane. This is the same thing as solvent. Solvent, right? Cyclohexane was a liquid, which this is the same thing as solvent. So I really need this number here. But this is not in kilograms. They say we should have it in kilograms. So you see the second number I highlighted here? Let me highlight it orange so we can look at it, the different number. We need that orange number, the 19.47 grams, that's the solvent. We need that to be kilograms so we can multiply it here, right? So for right now, I'll leave it as kilogram solvent. So we need to make that number a kilogram. So I'm going to go with from grams of solvent to kilograms of solvent. So this is going to be what? 19.475 grams. Convert this to kilogram. It's going to be 1 kilogram over 1,000 grams. Let's see. Calculator. 19.475 divided by 1,000. Okay, so we're getting 0.01947. It's a lot of numbers, kilograms, right? So now we got this number here, which is this. I can put this back in here and actually solve for moles of solute. Okay, so moles solute equal 0.0926 moles over kilogram times 0.01947 kilogram. Okay, this and this cancels out. So we get our answer in moles times 0.0926. Now, as we're doing this dimension analysis, if you're somewhat feeling lost, what we're doing is manipulating the numbers, trying to get rid of units we don't want and bringing in units we want using dimensional analysis. So if a unit is something that we don't want and it's on top, we're dividing it out. If it's on the bottom, we are multiplying it out. Okay? And then rearranging stuff until we get the unit that we want. And that's why it's important to really know what your desired unit is. And of course, in the middle, if we have a formula, we're bringing that in, right? So I'm trying to get moles. Wait, did I get moles? Okay. Getting a very small number. It's written scientifically on my calculator 1.803 times 10 power negative 3. Does anybody else get that? Is there a point there somewhere, Bryce? Like between 1 and 0? Okay. Yeah. That's what I get. So, wait a minute. What were we looking for again? I know. In chemistry, we do all this stuff, and then you're like, wait, what am I doing again? We're looking for the molar mass of the unknown solute. Okay. We already had the grams is up here, the yellow part. All we needed was the moles. Oh, we just got the moles. Okay. So we can assemble those together to get the number. So molar mass is going to be grams over moles, like it says so up here, right? So our grams of the solute is here, 0.37, 0.37, that goes with grams, over the moles is the number we just got, 1.803 times 10 power negative 3. Now, I'm going to tell you right now, this is not right. I mean, I shouldn't say that. Okay, we'll see. Divide by 0.37. I'm going to do an inverse. -1. Okay, so when I work mine out, I get a molar mass. This pen is, my Apple Pencil is glitching. Okay, there, it's working again. Molar mass is 205 grams per mole. I mean, it looks like a legitimate molar mass, right? It's too high because I told you in the beginning that this number is not exactly right. It's a little bit off, but yeah, it's based on how I read the table. But according to what I read, this is my molar mass. So over here, I write molar mass 205 gram per mole. So you guys will work and get the right molar mass. Okay, let's see. Somewhere in here is supposed to mention that the correct molar mass is 128, I think. Oh, yeah. The accepted molar mass of the unknown is 128.17 grams per mole. So the theoretical is 128.17 grams per mole. Okay, so we're supposed to figure out the percent error. And percent error is equal to the absolute value of the actual minus the experimental. You know, can I change these words here? I should say theoretical. I think it's better to say theoretical. No, I can't. Oh, read only. Okay, well, okay. I'm gonna write it here. Instead of writing actual, because actual is sometimes used as their experimental. This is gonna be theoretical minus experimental over theoretical times 100. Okay. So this is a theoretical value. This is the experimental value. So I'm going to figure out how correct, as you can see, versus, yeah, I want to see how correct I am. So theoretical value is 128.17 minus 205. I mean, I overshot over 128.17, right? And these vertical lines are absolute value. That means whenever you're done, just get the positive value of that. Really, we need it for the top part, not the bottom part. Find the difference here and then take the positive value of the difference times 100. So I'm going to find the difference between these two numbers. 128.17 minus 205 equal negative 76.3.83. Okay? We're taking the positive value of that, so it's going to be the positive value divided by 128.17 times 100. Times 100. Okay, so I was 59.9% off target. Considering the issues I was facing, y'all saw what happened. Not bad, right? But yeah, so my percent error here, I'm not come rounding up to 60, but who wants to do that? So 59.9%. Okay. Any questions about this? Now, of course, this is not the right answer. So if you put this in, you will not be right. Because, I mean, you can see how wrong it is, right? I mean, correct? Yeah. When you actually draw it very better, it will look better. Yeah, when you draw it better, you see how it works out. It's just I was trying to use my free hand to work this out. Does somebody have a question?
So we do all this lab on Excel, right?
I mean, you can do it on Excel. You can print it out. I was just doing it here because it's easier for me to show this to you. If you want to do it on Excel and then submit it on eCampus, that's fine. If you don't like that and you rather do it a hard copy and submit it in lab on Tuesday, that works too. I don't want to force you to do it online when this is not an online class. But if you want to submit it online and you're comfortable with that, sure, go ahead, do everything I've done, draw the best fit line, submit it online. But what you need to submit, you need to submit the graphs, right? The two cooling curves that you drew for these. You want to draw that and show how you're drawing the best fit line. So let me give you an example since what I did was average, maybe even below average. Let me show you no. The graph for its explanation. This is an example. Oh, this one here, this doesn't look realistic at all. Sometimes this is what happens in the lab, right? It looks more like this. So let me see if I can zoom this in. Well, they did something else, right? Okay, but this is a graph that shows you an example of a freezing point depression between the solvent only and yeah. So the way this worked out, you see the beginning is all straight. It's very, very good. You see they got that right here, and they drew the best fit line for the first few data right there, and then where it kind of stabilized, they do the best fit line. So in the end, it looks more like the freezing point. If this is straight, then it's more like the average of these data sets right here, where it tapers off. Okay, but you want to draw that and illustrate that. The freezing point will be this part right here. The second one, though, it kind of slopes down. So what you're looking for is this part right here. That's the better freezing point. It was just hard for me to illustrate that with the graph. And so when you get the freezing point for the second one minus the freezing point for the first one, you get a better delta T, right? It's the gap between the second, well, the first minus the second one. So the issue, the reason why we had a huge error, right, 60% error, is because of the way I drew the bottom one. I think the top one was a lot better. The bottom one, my hand shaking as I'm using my mouse and all this stuff. But I feel like if you draw it better, and I showed you right about where it should hit, it's not the number down here, but it should be somewhere up here, then it will help you see what the difference is. Okay. And of course, when you work it out, you have less error than what I had. Any questions about the lab? And so even though I have completed this on here, y'all know this is not, I mean, this number is correct. The part that's not correct will be, since the molarity is influenced by this, let me see. Let me remove these ones right here so we can see. But just in case you're wondering, this part should be good. This part should be good. Freezing point depression, that was given to you. The freezing point of cyclohexane, I think it's close to this number here. So 6.4, 6.3, that should be good. Anyone here? This is okay. You can double check. I'll say double check this one here. So double check that. I'm gonna highlight what you should double check when you do it yourself. This should be fine. Double check this. And for that reason, since these influence each other, double check that. Recalculate that. Recalculate this. Recalculate that. So essentially all of the things I've highlighted, just in case you're wondering. You want to recheck those because those will adjust when you get your readings correct. Okay. Other than that, I think I am done for the lecture and the lab. Does anybody have any other questions?
Can you help me with some of the homework problems?